So if you remember in the previous video, we looked at scatter plots and how it could be useful to look at how one variable covaries with another variable. But if we want to do it in a way that is not graphical, but more mathematical, one thing that we can calculate is the covariance. And the covariance is a measure of the joint variability of two variables, x and y. And the formula for the covariance is as follows, so denoted as cov between x and y, and it's 1 over n minus 1 times the sum between I is equal to 1 to n of xi minus x bar times yi minus y bar, where x bar is the sample mean of x and y bar is the sample mean of y. Okay, so there's the product of the difference between x and the sample mean and y and its sample mean. But to make it a little bit more concrete, let's have a look at an example. So let's say that this is my x variables. I have three observations. I have 23, 42, and 13. And for y, I have 78, 183, and 54. Okay. So if we calculate the sample mean of x, we get 26, and the sample mean of y is 105. So the way we calculate the covariance is as follows. So we have 1 over the sample size minus 1. So 1 divided by 3 minus 1 times, and then we take the first observation of my x variable, so 23. We subtract the sample mean of x, which is 26, and we multiply by the first value of y. So for my first observation, the value of y is 78. So I have 78 here, minus the sample mean of y. Okay. And we do that for every single observation. So for example, for the second observation, x is 42. We subtract the sample mean of x times 183, which is the value of y for the second observation, minus the sample mean of y, etc., etc. And when we're done with the calculation, we get a value of 996. Okay. And one thing we might have noticed is that when x is small, y also tends to be small comparatively to the values that it can take. Okay, so we can see that 13 is the smallest value of x, but it's also the smallest value of y. And similarly, 42 is the largest value of x, and it's the largest value of y, and 23 is in the middle for x, is also in the middle for y. Okay, so in this case, it seems like the x and y covary positively. And this is what is expressed here, because we can see that the final number that we get when we calculate the covariance is positive. Now let's have a look at a different example. So this time we get 17, 67, and 39 for x, and 54, 15, and 33 for y. Okay, and one thing we can see is that when x is small, like for example 17, actually y tends to be very large. And similarly, when x is very large, 67, y is very small. Here 15 is the smallest value of y. Okay, so that's the first thing that we may notice whenever we look at data, is that whether there's a pattern of covariance, and we'll see that with the calculation, we'll get exactly the same insight. So the mean of x, so the sample mean of x is 41, and the sample mean of y is 34. So we calculate the covariance exactly as before. So remember, it's 1 over the sample size minus 1, where the sample size is 3. We take the first observation, look at the value for x, which is 17, minus the sample mean of x, times the value of y for the first observation, 54, minus the sample mean of y, which is 34. Okay, and we do that for all observations. And here, what we obtain is a negative number. Okay, that means that the covariance between x and y is negative. So how do we interpret positive covariance or negative covariance? So if high values of x associated with high values of y and low values of x with low values of y, then we say that the covariance is positive. And if low values of x are associated with high values of y and high values of x with low values of y, the covariance is negative. But one issue with the covariance is that its magnitude is actually quite hard to interpret. And the reason why it's hard to interpret is that it depends on the unit of measurements of the two variables that we're interested in. Okay, if we just change the unit of measurement, so we don't change anything apart from the way we measure those variables, we'll get a different value for the covariance. Okay, so that in a way is not ideal, which is why very often what we'll calculate in practice is Pearson's correlation. And Pearson's correlation is just a normalized version of the covariance to make sure that the magnitude is always between -1 and +1. Okay, so the formula for Pearson's correlation is the covariance between x and y divided by the standard deviation of x times the standard deviation of y. And the way we write Pearson's correlation is just r, x, and y. Okay. And Pearson's correlation should really be used with interval variables. Now, a correlation of +1 indicates that there's a perfect increasing linear relationship between x and y, and a correlation of -1 indicates a perfect decreasing linear relationship between x and y. And a correlation of 0 indicates that there's no linear relationship between x and y. And the closer the coefficient is to either -1 or 1, then the stronger the correlation between the variables. Right? So if we look at those different scatter plots, we can see that here there doesn't seem to be any pattern in the data, and that a horizontal line might be our best guess for the relationship between those two variables. Whereas in this case, there's a clear positive correlation. It's even stronger here because we can see that all the points are closer to my straight line. So the straight line is a relatively good approximation in this case to what's going on in the data. And here we have a strong negative correlation between the two variables because we can see that the slope is negative and that all the points are quite close to the line of best fit. Now, Pearson's correlation is not going to solve all of our problems either, because one thing to remember is that it only tells us the strength of a linear relationship between two variables. Okay, so here I've shown you different scatter plots with different types of relationship between the variables. And the Pearson correlation coefficient is the same, 0.816, for all the graphs above. And as you can tell, we have extremely different relationships between x and y in all four graphs. Okay. In this case, it seems like this one might be a mistake because it seems like there's a perfect linear relationship between x3 and y3. In this case, actually, this one is an outlier, and it's unclear if there's any relationship between x4 and y4 in reality once we remove this observation. Here, it's a clear nonlinear relationship between x2 and x3, and so the linear approximation might be this, but actually it shows that we should model it differently, and that maybe the Pearson's correlation is not the most appropriate measure, since it only focuses on the linear relationship between two variables. And in this case, well, it might work relatively well as an approximation of a linear relationship between x1 and y1. So it's in practice very useful to examine the scatter plot whenever you have two variables and you just want to measure the correlation between those two variables. So that's it for today's video. And in the next video, we'll have a look at other types of correlation measures.